Hello and welcome back to my channel. Today we'll be discussing the conservation of energy, or more specifically, the law of conservation of energy. Now, you may have heard the term conservation of energy before, but what does it mean? Well, the conservation of energy means the total amount of energy in the universe is conserved. So that means all the energy that we have in the universe is conserved. It's not lost nor gained. So it means, if we're going to write it out, all energy in the universe is conserved. Now that we understand this, we also need to understand that energy cannot be created or destroyed. We cannot create energy, nor can we destroy it. The only thing we can do with energy is we can change it into different forms. Energy can only be changed into different forms. So cannot be created or destroyed. Only changed into different forms. Now, what types of energy or what forms of energy there are? There's many forms of energy, such as we talked about mechanical energy and kinetic energy, gravitational potential energy. There's all types of forms of energy. So we need to keep in mind, though, that energy cannot be created nor destroyed. But what does this really mean in terms of our physics unit, our physics course? Well, that means that if we have the symbol for energy, which is just E, remember in the previous units we put EK or EG. Well, if we want to just talk about energy as a whole, we know it's going to be E. Well, E1, if we have one energy or one form of energy, let's say we had the kinetic energy in my hand if I'm bringing them together. Then, as soon as my hands hit and they clap, that kinetic energy turns into sound energy, which is now then changed the type of energy we have. So that means, but energy is, remember, always conserved. So our E1, or our energy 1, will be equal to our energy 2, because energy cannot be created nor destroyed. So our energy is always conserved. Similar to how you may slam your door. Before you're slamming your door, there's kinetic energy in the door, but that kinetic energy is then transferred into sound energy and other forms of really energy you may experience. So we cannot really lose energy, nor can we create energy. Now, how does this work? Well, remember the units for these are just joules again, because we're talking about energy. And E is really equal to EK plus EG, our two forms of energy, our kinetic and gravitational potential energy. So that's what our E is equal to. And if we're looking at what it'll equal to, if we're looking at this formula, what this really equals to, well, E1 is equal to E2, which means EK1 plus EG1 is equal to EK2 plus EG2. And then we can further break this down to the actual formulas for these. We can write 1/2 mv squared 1 plus m1gh 1 is equal to 1/2 mv squared 2 plus mgh2. Really, you won't be working with different masses, so you don't really need a 1 on the mass, but you really need make sure you put your variables down here to differentiate your equations. And from here, depending on the question, we will see different things maybe drop out, or we have to rearrange to find different things. So from here, let's look at a example question, and you can see how it applies to what we learned up here about mechanical energy. About conservation of energy. So let's get into our given right away. We have the mass, so it says a 65 kilogram diver dives from a 10-meter high platform into the water below. What is his mechanical energy when he is on the platform before diving? So we remember that mechanical energy just means the sum of the kinetic and gravitational energy. So we know that the mass is going to equal 65 kilograms. Remember, we don't really need to define a direction because energy is a scalar. It's not a vector. So that's why we don't put vector signs on our velocities either. But now that we have the mass, we can go his height, our h1, because he's initially on 10 meters high on the platform. So our h1 is 10 meters. He jumps into the water below. Our h2 is going to equal 0. Because if we have a diver right here, he's standing on top of a diving board. He's 10 meters this way, right? And if he's 10 meters, and if the water is right here on the ground, we're assuming the ground to be 0, and he's 10 meters above the water. So that's why we can assume that h1 is 10 meters, while h2 is just 0 meters. Because the ground would be 0, anything above the ground would be a added distance. So now that we have that, what is mechanical energy when he is on the platform before diving? So we can also just write quickly our gravity, which is just always a constant, 9.8 meters per second squared. And it also says he's the diver, so it says before he dives, right? What is the mechanical energy before diving off the platform? So before diving, he's probably just standing, so we can just assume his velocity wants to be 0. So we're required to find, we're looking for, it says, what is mechanical energy? So EM. And if you remember EM, what EM is, well, EM is just EK plus EG, our kinetic energy with our gravitational potential energy. So now we can calculate what our kinetic energy will be when he's on the platform. Our EK will be 1/2 mv squared plus our plus our gravitational potential energy, which will be mgh. So now that we have this, we can assume that our 1/2 mv squared, because initially at the top of the diving board, he doesn't have any kinetic energy. He's just standing there. So this will drop out, and you're left with EM is just equal to mgh. So now we can just calculate our mgh. We can go into our solution, and that will be EM is equal to 65 kilograms multiplied by 9.80 meters per second squared multiplied by 10 meters. Now we can just put this into our calculator, 9.8 times 10, and you get around, your EM should be 6,370 joules, remember, because we're working in energy, so our units will always be joules. And we can round this off to 2 significant digits, so we can go 6.4 times 10 to the 10 to the 3 joules. So this is our final answer. This is his energy before he dives off the board. Part B of this question says, what is his mechanical energy when he reaches the surface of the water? Okay, so let's look at this question right here. We're going to look, before we were looking for what his mechanical energy was when he was standing up here. But now we're looking for his mechanical energy right at the surface of the water, so right about here. What is mechanical energy? Well, remember our previous formula, EM is equal to EK. Well, remember, you want to put 1s and 2s on your EK and EG to make sure everything's organized. So we can put EK2 plus EG2, and now we can sub in our values, 1/2 mv squared plus 2 plus mgh2. And if you remember right here, we defined mgh to be 0, so we can just drop that term out completely. Now you may wonder, oh, great, we can do this question now. But the thing is, we don't have velocity. So if we don't have velocity, how are we really supposed to figure out what EK2 is? Well, if you remember what I talked about before, how energy is always conserved, E1 is equal to E2. We can go E1, which is equal to EK1 plus EG1 is equal to EK1 plus EG1. Well, if you look here, our initial velocity, because if we convert all of this to the proper notation, so if you convert all of this, remember our initial velocity was 0, so this drops out to 0. Our second height was 0 as well. So this drops out to 0. So now we have mgh is equal to ek1. So we know our mgh is equal to our ek1. So now we have what all this whole term is. We know that em is just equal to mgh. And then again, if we look here, that's the same thing we had on the first part right here. So if we solve, again, we're going to get 6.3, 6.4 to two significant digits. 6.4 times 10 to the 3 joules. And again, we get the same answer. Why does that happen? Well, the whole point of this is to remember that energy is conserved. Our energy at the top of the board will be the same as our mechanical energy on the bottom, because if we're standing up here initially, we have gravitational potential. We have mgh. That's our energy. That's our gravitational potential. But when we dive off, that gravitational potential gets converted into mechanical. Now we have mechanical energy, and that mechanical energy is still the same as what our gravitational potential is, because E1 is always equal to E2, because our energy is always conserved. So that question really illustrated how energy is always conserved, why it's really relevant to what we're talking about. Now let's look at this next question. So it's kind of given. It says a 2.5 kilogram rock, so our mass is equal to 2.5 kilograms, is dropped from a height of 20 meters. So our H1 is equal to 20.0 meters. Ignore air resistance. So it says, what is the rock's final velocity? What is the velocity of the rock just before it hits the ground? So if we're holding the rock, if we're assuming that we have a person here, we have a person standing here, and they're holding a rock, and then they drop it. So initially, when they're holding the rock, the V1 is going to be 0, correct? So then he drops at a height of 20 meters. He'd probably have to be on some type of platform. But initially, the height is 20 meters. We're looking for the velocity of the rock. We're looking for the velocity of the rock right before it hits the ground. So if this is the ground right here, and it's right near the ground, the H2 is going to equal 0. So now that we know that, we know what M is, we know what H1 is, we know what H2 is, we know what V is. Now we're really looking for V2. How are we going to get V2? Well, remember, energy is conserved. How can that help us? Answer analysis. The first thing we're going to do is E1 is equal to E2. Why? Because energy will be the same. So we can write EK1 plus EG1 is equal to EK2 plus EG2. Now that we have this, we can write 1/2 mv1 squared plus mgh1 is equal to 1/2 mv2 squared plus mgh2. From here, we can look at what terms will drop out. Well, our initial velocity is 0, so this will drop out right there. Our second height is going to be 0, so that will drop out right there. So that means we're really left with mgh1 is equal to 1/2 mv2 squared. So we're looking for this right here. So from here, it's just simple rearrangement. We're going to try to move this 1/2 to the other side. So we're going to multiply by 2. What's connecting this mass with this velocity? It's multiplication. That's the operation. So we can divide by m. And now we still have a square root here. So we're just going to take the square root to get rid of this square root right there. So now we have 2 mgh divided by m. Take the root is going to equal to v2. Well, if you notice, we have an m on the bottom and an m on the top. And they're like terms. So we can just drop out the m completely. And we're left with 2 times gravity times h with the root is equal to v2. And now we can go straight into our solution. So our solution right here, we root 2 times 9.80 meters per second squared times 20.0 meters is equal to v2. And from here, this is just calculator work. So we can take 2 times 9.8 times 20, and you should end up getting 19.79 meters per second, which is equal to v2. So round off to 2 significant digits because we have 2 here. We actually have 3 here technically. but in our given we have 2 right there. So we should round off to the most least significant digits. So we should round off to 2, which will equal to 20 point. You can put a decimal right there, and then these 2 with significant digits. You'll have meters per second is equal to V2. And that's how you use conservation of energy and how it applies to these questions. Most of the questions that you will do, you will often start off with E1 is equal to E2. From here, you just have to rearrange these questions, like rearrange to get maybe height, maybe you have to rearrange to get the initial velocity, maybe the mass. A lot of these things you just have to rearrange. And oftentimes you'll notice that we actually have an M in all of these terms. So you can just drop out M in your terms, and you don't really need to worry about that. That's the one thing about this. You don't really need mass. So if you're ever dealing with a question you don't have mass, you usually don't end up needing mass in the question. But in short, that's just the law of conservation of energy and how it applies to our physics problems here. I hope you enjoyed the video. I hope you learned something. And remember, physics rocks.